நான் அப்ப அட்மிட் பண்றேன் சார். We'll start by 6:30.
Good evening to everybody. On behalf of Institution of Engineers Tamil Nadu State Center, I welcome today's speaker, Mr. Elangovan, Associate Chief Engineer in Technip FMC India Limited. And then I welcome all the participants today, today, and our committee members, other fellow engineers. Today, this topic is process safety in oil and gas projects and introduction. The last week, the two incidents happened. One is Vizag and Neyveli. I think this topic is the right time we are putting this topic. So now the Gokul is a scientist from ISRO. He will introduce Mr. Elangovan for this session. Mr. Gokul, yes, now take over.
Yes, sir. Thank you, Chairman. So very good evening to all present here. I think we are taking up a very good session from our IEI TNSC. So we had a session from energy, and we had a session from blockchain, from 3D, and last week also we had a session from Ramco system. So I think every field, I think IEI TNSC is giving a chance, and they are presenting a lots of work. Today we have our chemical engineer, who is Elangovan, who is an associate chief engineer, process safety. So he's from Technip. So we welcome Mr. Elangovan also, and he's also an IEI FI member. So very great to see about his profile. He is bachelor's in chemical engineering, also a diploma in petroleum engineering, and he had almost 18 years experience in PDO Shell approved technical safety engineer. Experiences spans on a successful execution of process safety HSC and loss prevention scope for feasibility feed PMC projects onshore and offshore. He also included his experience on onshore and offshore field survey and data collection. He worked in various countries like in India, Italy, USA, UK, Qatar, UAE, Oman, and he also has a very good safety certifications from HAZOP leadership, QRA, non-reactive relief design, environment impact assessment, and he has more chemical software expertise also, which includes PipeNet, Shelf-Ride, Aspenizers, and many more. He has a professional membership which includes including from our IEI, IACHE, AICHE, IIPE, and ICHEME UK. So I think we got a right speaker at this right scenario, as our chairman said, since we are in COVID-19 and more chemical industries are get to opening up. We are seeing so many safety ASOPs are happening up. So definitely I think we have a right persons who is currently working in Technip India Limited as an associate chief engineer process safety. So thank you so much, sir, for your presence here to share your expertise as well as your knowledge to our engineering community. So thank you also for all our members who are joined. So can I ask our Elangovan sir to initiate this presentation? Sir, please go ahead.
Thank you, Gokul, and thank you, Mr. Ramdas. Thank you for this opportunity. And the team who have participated in this webinar through online link, I appreciate your efforts. That was a fantastic Sunday evening, sacrificing your movie time to attend this webinar. I ensure that this webinar will be of interesting and it may have some takeaway for you to your career. So I will put up the slides in such a way to make it interesting. Okay. So before getting into our webinar, I will just give you a brief introduction where I am from. That is the company for which I am working for. That will give some background. Okay. So I am working for Technip FMC. We are into the business of three segments. That is onshore, offshore, surface, and subsea. Onshore, that is related to the platforms which is coming up in the sea. That one we have the experience with the deep water and the shallow water platform. platforms and the FNG floating LNG ships. And on the onshore, we have experience in mining, metals, LNG, petrochemicals, refining, and hydrocarbons. And in the subsea, that is below the sea surface, we have businesses into the upstream activities like SURF, SPS, and the flow lines and other things. And on the surface side, again, we are into the upstream activities, supporting the wellheads, jetty loading arms, and all those things. This is the area we are working on. And within this organization, I am into the process safety department. I'm looking after the process safety requirements for the mainly for the onshore and offshore projects. So this is the brief introduction for the company. So before going to the webinar, I am putting up some of the keynotes. The first thing, this is a presentation where we are going to discuss about the introduction. This is not the detailed presentation. My intention here is to touch upon what are all the process safety activities, typical activities and tools used in the typical oil and gas project. So it will give you the idea of what is what, and it won't give you the detailed one. So given that we don't expect any calculation or exercise in this webinar, so just relax and listen to the presentation and enjoy the presentation. And the third point, feel free to stop and ask questions. This is my regular way of addressing the questions, participant questions, if it's a face-to-face meeting. Unfortunately, since this is a webinar, so I need to change this condition. You need to post your questions in the chat box. Hopefully, Google or somebody from IEI, they will have the track of all these questions. And I will try to answer as much questions as possible at the end of the session, given the time limitation. So this is a pre-note. And hopefully all your speakers, the mic are muted. This is just to have that single conversation so that everybody can understand what we are discussing. So as you said, you have the time to raise your questions in the chat box that can be addressed at the end of the session. Okay. So as the attendee of this webinar, what I can get out of this webinar. So what is a process safety? You can get some understanding what is a process safety. And most of the time, the people from the field and mainly from the other disciplines within the engineering organization, they will confuse process safety with the personal safety. So we will give some differentiation, how the process safety is different from the personal safety. And the third point, as the title says, we are going into the concepts and tools which are applicable to the oil and gas projects. And to get some real-time experience, what I thought is, instead of explaining these tools, why don't we take up with a hypothetical project example? Let us assume one project, and we will apply all those tools. What I am going to discuss in this webinar into that project, and we will see how best we are getting that understanding of those process safety tools. So this is the takeaway for you people attending in this webinar. Hope you enjoy this session. Let's get into the webinar. So let's define what we are going to define. So as the title says, we are talking about the process safety. Our first point is to define the process safety. So when you just Google the in the Google, if you enter this process safety definition, I am sure you can get thousands and thousands of definition. Okay, so this will differ from country to country, organization to organization. One of the foremost organization on the process safety sector is Center for Chemical Process Safety, that is AICHE, which is situated in USA. So one of the definition from CCPS is the protection of people and property from episodic and catastrophic incident that may result from unplanned or unexpected deviation in process conditions. So some of the key terms here is unexpected deviation from process conditions. So we are running the process for the fixed process conditions. If something deviating from that one, which may result in an episodic or catastrophic incidents, and which may result in a damage to the people and property. So those incidents which may result in a damage to the people and property, which is in the nature of episodic. Episodic means a chain of reactions, chain of events, and catastrophic, that is a sudden damage or other things. So those incidents are considered as a process safety incidents. This is one way of defining the process safety. To add a little more clarity, I am bringing in one more definition from Energy Institute, that is a UK organization which is working into that HSE aspects of the energy industries. So I am getting that one. What it says, it is little bit elaborates the CCPS definition. Process safety is a blend of engineering and management skills. So here the keyword is that is not only the engineering, the management also should have the responsibility to implement the engineering things. So it is an engineering and management skills focused on preventing catastrophic accidents and near misses, particularly structural collapse, explosions, fires, and toxic releases associated with the loss of containment of energy or dangerous substances such as chemicals and petroleum products. So the keyword here is, as you see here, the loss of containment of energy or dangerous substances. As you see here, we are, as a process safety, we are looking into the areas how to eliminate the loss of containment of dangerous substance. In the dangerous means it may be a flammable or toxic. As I say, it is a loss of containment of energy. For an example, if you have the high pressure air receiver, there you have the stored energy of high pressure energy. If something happens to that vessel, if there is an the explosion happens to that air receiver, what will be the damage? So this is not only to the flammable and toxics, this is also related to the loss of containment of energy. So as it says, it is a loss of containment of energy and dangerous substances. You can say that process safety cannot be applicable only to the oil and gas. You can apply these concepts and the tools to the any industry where you are handling a dangerous substance, which may be flammable or toxic, or you have the contained energy. For an example, automobile industry. Yes, process safety concepts are applicable for them also because they have the pneumatic system, hydraulic system, and hopefully the steam, I don't know, and hopefully the fuel gas for heating their furnaces and other things. So these concepts not only applicable to the oil and gas, that can be applicable to any industry where you have this condition, loss of containment of energy or dangerous substances. Hope this gives some idea what is process safety. So now we move into the further how we are differentiating process safety from the personal safety. I am giving you one example here. So this is one of the cartoon. It's showing the typical industrial activity. As you see in this cartoon, you can find a number of unsafe acts or hazards. For an example, there is a chance for this spanner hitting into the person's head. He is not wearing the helmet. Okay, this cyclist parked on the way of escape, and he is standing on the handrails. So you can list out number of such safety, unsafe conditions or hazards. As you see here, this will be the full list of unsafe conditions. But can you fit these unsafe conditions into the definition of process safety? So what process safety says definition, what says it isn't loss of containment of energy or loss of containment of dangerous materials. By seeing this picture, we cannot see that all these safe, unsafe acts are related to process. I say that we cannot means we don't know what is material handled in this process section and what are the hazardous properties of those substances. Without knowing this, we cannot define whether these unsafe conditions are falling under the process safety. But definitely it is sure it is a personal safety. Given that, by seeing this picture, I can able to point a couple of acts which may fall under process safety. For an example, these two. Here you can see that there is a flange is missing here. If a fluid is introduced in this vessel, that may result in a loss of containment. Definitely, this is a process safety incident. And here, if you see here, this is an what is it? The flange. It is an hanging in a type. So if this is falling, this dropped object, this object is dropping into live lines, which may result in loss of containment, then I can say that this is a process safety activity. So by seeing this example, hopefully you can identify, differentiate what is personal safety and what is process safety. As defined, it is a loss of containment of energy or loss of containment of dangerous materials. So this is a key takeaway. Hopefully hereafter you can able to clearly distinguish what is process safety and what is personal safety. With this background, we are moving into application of process safety into oil and gas projects. Here I have given the typical life cycle of a oil and gas project. So generally we'll start with the concept. So I have one product in mind. So I want to develop a plant to produce that product. So that is the concept stage. The concept is what I'm going to do. I need to fix up what is the capacity of my plant, what is the basic things, very basic things, what area of land I require, what is the key equipment for those things. Then the project moves into the basic engineering, where some more details is added into the design and into the detailed design stage, where everything is fixed up, freezed, the design freeze stage. Then it goes to construction, then it goes to commissioning, and after this commissioning, it is handed over to the owner, who is the operator of this plant. The operation is going on. After some time, the owner says he may need to introduce a new product, or he may need to increase the capacity, or he may need to address some issues, design flaws, which is happened in the basic engineering of the detailed design. Then he will go into the modification phase, where this improvement to the plant, or improvement to the asset, or improvement to the product, product portfolios, the new products, all those things are happening. So this is an cycle activity, operation and modification. So for every plant, there is a phase that need to be decommissioned, because we cannot foresee the demand for the product for long. Generally, what we do in oil and gas industry, we will design for the plant for 20 to 50 years. This is the general philosophy what we are on. So that means that we design the product plant which can withstand up to 50 years. After that, they need to go for the improvement, or they need to decommission, go for the new. So this is how the typical cycle goes on. In oil and gas, we call this whole thing as an engineering, procurement, construction, EPC. So these first three cases, concept, design, basic design, detailed design, that is called engineering. And under the construction, we go for procurement, construction. So the engineering contractor typical work is up to these phases: concept, basic design, detailed design, and construction. Then the rest of the phases will be handled by the owner operator of the particular plant. So given that, with the title Process Safety Aspects in Oil and Gas Projects, as I am from the engineering company, the whole webinar will be concentrating on these three steps of the EPC project. That is the concept stage, basic design stage, and the detailed design stage. Okay. So what are all the process safety aspects typically applicable for the oil and gas projects? We will start with the concept. The very first thing what we implement for the project at the concept stage is ISD review. That is the Inherent Safety Design Review. We are going to discuss further in the coming slides. And the next will be the HAZID and HAZard, which will be typically taken care in the basic design stage, and the HAZOP and LOPA. This is something and follower. It can be taken in the basic engineering as well as in the detailed design stage. And you are in generally at the detailed design stage. And these four things are typical review procedures. So what I'm saying is the review procedure is we are assessing how safe the plant what we are designing. Okay. And apart from these review procedures, we have fire and gas detection, which is an added protection layers. We are going to discuss about these things. And the hazardous area classification, active fire protection, passive fire protection, engineering control of noise, safety layers. So this will give the overview what are all the safety concepts applied in the oil and gas project. So we are going to discuss all these key elements in the subsequent slides. Okay. So as I told earlier, we are going to discuss these key elements with the help of a hypothetical project. I am not going to explain to you as a theory. We are going to apply this concept in a sample projects. Okay. So are you ready for handle your project, typical sample project? That's it. Okay. So we have the client who is having a plan, and he is having the idea of putting up a diesel storage system. Design a facility to store diesel fuel in bulk and distribute the same to various end users. End users means where this diesel is going to be used. Typical examples may be the diesel generator, boiler, instrument, etc. within the plant. So this is the requirement. Let us assume this is a typical oil and gas project, and this is a client requirement, and how we are going to design safer plant by the application of the process safety concepts, what we discussed in the previous slide. Okay. So once this requirement came into the any APC company, the first person getting into the job is a process engineer. So you need to speak to the client, what is this requirement, assess the requirement, and get up with the very basic things. Okay, so now we are entering into the concept phase. So what we have, client is asking for the storage. So typically we need to have the storage tank for the diesel, and it is going to be distributed to the multiple end users. So end users may be distributed across the plot plan at the different location. So we should have some source to generate a pressure so that we can deliver the diesel into the end users. So obviously we need to have the inlet to the diesel, that is and where we are getting the diesel. And as I told, we need to have the distribution pump and the pipe network to distribute the thing to the different users. So this is a concept stage. The process engineer, as a person who is the first person entering into the project, he need to get a consultation with the client to get fixed upon what is the demand for this diesel based on the end user's requirement. And as I told earlier, based on the location of the end users, what is the my source pressure required. So these are the two key components that need to be fixed up in the concept stage, as well as the key equipments required. In this case, a diesel storage tank and a distribution. Okay, process engineer done his job. Then he is looking into me, process safety engineer. Hey, Elan, this is my concept design. Can you look into that design from the process safety perspective? Yeah, okay, we can do it. We have the inherent safety design review. Let's go for the review. So, what is the inherent safety? A process has inherent safety if it has a low level of danger, even if something goes wrong. Okay, this is the definition. There is one very good proverb. If you don't have anything in your pipeline, there is nothing going to leak. That means that if your residual risk itself is very less or negligible, then there is nothing harm going to happen if something is going to leak. Okay, this is the concept of inherent safety. So what we are doing here, we have the keywords like what is given here in red. There is a minimization, substitution, moderate, and simplify. And this is a team activity where the team from client side as well as from the getting contractor side need to assemble, and they need to do the brainstorming based on these key concepts. That is a minimization. For an example, what minimum volume of the tank? See, this diesel tank can be sized to store the diesel for a 1 day consumption, or 1 week consumption, or 1 month consumption, or 1 year consumption. There is no limit for the capacity of the tank, but the risk for each case is different. For the 1 day, for an example, it is an 100 liters means for 1 week it will be 700 liters. So if there is a leak happens, in the both cases, the consequence will be different. For the first case, at the worst case, we may be having the loss of containment of 100 liters of diesel. But the second case, we have the loss of containment of 700 liters of diesel. So we need to agree on what minimum size of diesel tank we can have to satisfy the end client requirements. Okay. Substitution. Why diesel? Why not natural gas? So we need to brainstorm why diesel is required. See, the end user is a generator, a boiler, incinerator. Why not we have the natural gas? What is the advantage of natural gas having the diesel? For an example, if it is a diesel, we need to have the storage tank, and if there is a leak happens, it will result in a pool formation in the ground. If it is a natural gas, we most probably may not need a storage tank. It can be a pipe system, which can be piped directly to the end users with the regulation or flow measurement or the control system in between. If there is a leak happens, it will be dispersed in the air for the minor leak, I'm saying. Okay. So is there any advantage? So this is the way we need to brainstorm to substitute and moderate. At what temperature and pressure is it possible to reduce the pressure? Because if you have the high pressure means you have the high consequence. See, assume the leak which is happening from the pipeline, which is maintained with 1 bar, and the same pipeline if it is maintained with 10 bar, what will be the worst case? The 10 bar, definitely, because the source pressure is high. Accordingly, your loss of containment will be high and the consequence effects will be high. So how best we can optimize the temperature and pressure? Simplify. Again, why we need this tank and the pump? Why don't we use as a distributed pipeline from the source itself? Or are we able to eliminate the storage tank or the pump? Is it possible? Because unwantedly we are storing the flammable material, not the flammable, combustible material in the storage tank, in the bulk storage tank. Are we able to eliminate this thing? So this is the way a typical ISD workshop will progress. This may be looking simple for the diesel tank. Let us say the recent example of HAZD. If we apply these things, there can be number of improvements can be done for this HAZD incident. For an example, minimization. From the news, you may understand that the tank is around some 2,000 or 3,000 liters capacity. Why such a huge tank is required? This huge tank resulted in the prolonged release of styrene and substitution. Why the styrene is required? Is there any alternative there? Moderate. What is the temperature and pressure? What is the operating temperature and pressure of the storage tank? Simplify. Why we need that intermediate storage tank? Whether we can have the pipe supply of styrene from the nearby. This is depending upon the source where the styrene is coming from. So this is the way. This ISD, the inherent safety design concepts can be implemented to any projects. As I told, as I recall again, this is a concept which can be applied to any industry, not only to the oil and gas. Again, if you take the automobile industry, the same concept can be applied to the automobile industry. So likewise, for any industry can be applied. Okay, good. We have the ISD workshop completed, and our process engineer happy. Now the project is moving into the basic design, and our process engineer added on some more details to that project. So this is what we have at the basic design. You can see the difference. Instead of a simple box, now it looks like, you see the difference. It is a cone roof storage tank. Okay, and we have the inlet, and our process engineer added an overflow line, and he had added a piping which is feeding into the pump and to the end users, and he had added a pressure indicator. So this is just an example. You don't take it as a rule. This is how the data basically, and this is not like that. This is depending on the process and the project what you are handling. I'm just bringing in the concept stage drawing what we had. Now you can see the difference how the project is progressed in terms of design. In the concept, we have only the inlet line and the rectangle box with the pump. Now we have the number of improvements to the design. Now we have decided the tank type will be the simple cone roof tank, and we have added a number of lines and attachments. So this is how the project is developed from the concept stage to the basic engineering. Now, perfect. Now again, process engineer comes to me and asks me what improvement you can do from the process safety perspective. Yes, you can do HAZID and NBIT. Okay, let's do. What is HAZID? The purpose of HAZID study is to identify the hazards that are present in the current design and the potential consequences if the hazards are realized. So again, we need to approach this HAZID as a keyword concept. It is a guide word review. We have the set of guide words from the codes and standards as well as the operating company's procedures. Accordingly, we need to again do the brainstorming. But when it compared to the guide words, what we use in HAZID and the ISD, it is totally different. Okay, ISD concept is to eliminate the hazard itself. Here to manage the hazard. Like the way we need to have these guide words. And when it comes to NBIT, it is similar to the HAZID, but however, the guide words are more and more related to the environmental hazards, the impact to the environment. Okay, for our case, let's do a HAZID for a simple one guide word. So this is the typical guide words what we use for HAZID. I'm just given the 4. There is a list of guide words would be there. You can refer any client document or ISO standards that you can get the total list of HAZID guide words. Let us talk with the process fluid release. Okay, so this is a typical HAZID worksheet. The guide word what we are talking is process fluid release. So what may cause this fluid release? One brainstorming point is a rupture of the tank due to corrosion that may lead to loss of containment of diesel. Okay, what is the consequence? Diesel tank rupture will result in a loss of containment of diesel, and upon ignition will result in a fire accident. So the loss of containment of diesel that won't immediately result in a fire incident. It should have your ignition source so that it will get into the fire. So what is the safeguard we have to prevent this consequence, prevent this cause and consequence? At present, based on our basic design, we don't have any safeguards. So what is recommended? The cause, we can say that the material, whatever selected, I can say that the existing safeguard, I can say that the material of construction of the tank, which will be suitably selected, and we have given the corrosion elements, and above the design thickness, what we arrived. So that is one of the safeguards, existing safeguard we can consider here. And the recommendation to prevent the consequence, we can provide the bund around the tank. So current design, we don't have the bund, so that if the vessel, the tank collapse, the diesel will spread across the platform until the content is exhausted in the tank. But if we have the bund around the tank, means we are containing the release within the bund. It is not spreading beyond the bund. Okay. So this is for one case, one guideword. Likewise, we need to brainstorm for the entire guidewords as applicable for this project in agreement. The guidewords, what is agreed with the client. So accordingly, we need to improve the design. So the same concept applicable for NBIT. I have not listed any worksheet for the example for the NBIT, but the concept is the same. The guideword may be different. For an example, emission to environment. What is emission? If we have the overflow line, it is open all the time. There is a diesel emission will be happening to the environment. So that may be the consequence. And what is the safeguards we have? What is the recommendation? Like the way we need to brainstorm for assaults, for the people property, as well as assaults for the environment. This is how we are progressing with it as it. Okay. Perfect. Now we enter into the detailed design stage. As you see here, our process engineer friend, he had further added on the engineering details to our system. As you see here, he had included the valve tag numbers for the items, and you can see here he had included one level switch here, high alarm, which is giving the LAH level high alarm, and he had included the temperature transmitter to measure the temperature inside the tag. He had included the level transmitter, the level indicator to measure the level. And he had included the level switch low alarm, and as well as he had included the tag numbers here. You can see how this project is progressed from the basic design, the detailed design here. See the basic design. We don't have the that is not the actual case. I'm just giving you for the example to see how the design is progressing. So the main concept is from the basic design to detailed design, the level of engineering, the detail of engineering will be increased. That is the whole concept. So perfect. We have the detailed design. Now, what safety, process safety improvements I can do it with the detailed design. Good. We have the HAZOP. Let's do the HAZOP for this process plant at the detailed design stage. What is HAZOP? HAZOP is called as a hazard and operability study. There is a two keywords here, hazard and operability. That is, this review not only looking into the hazard, and also it will look into the operability issues. For an example, if I have the strainer on the suction line of the pump, how I can do the maintenance for the strainer. For doing the maintenance, what provisions you have given in the design. So all those operability issues also discussed in this. That is the main difference between the HAZID and HAZOP. Okay, in the HAZID we look into the HAZard perspective. We are not looking more into the operability perspective, but in HAZOP we will look both in HAZard as well as in operability. So what is HAZOP? A systematic comprehensive analysis of plant design to identify the safety gaps which may lead to either safety or operability problem. During the study, the HAZOP team will use a guide word. Again, it is a guide word, but here the guide word is more and more narrow. This is here the guide word is a combination of deviation and parameter. We are going to see that what is the deviation parameter to identify the design flaws or the cause consequence and safeguards. So, what is the guide word for HAZOP? How it is getting here? This is the deviation. So what are all the deviation we can consider, and this is the parameters. Okay. So guide word is a combination of deviation and parameter. For an example, no flow. The combination is a no flow. That is a guide word. Likewise, less flow. This is another guide word. More flow, reverse flow. The second parameter is the temperature. Again, if you do the combination, no temperature, it won't be, because there won't be any no temperature. It will be either less temperature or more temperature. Likewise, pressure, less pressure or more pressure. Likewise, level, less level or more level. So we have the set of guide words now based on the combination of deviation and parameter. Let's do a sample HAZOP for the system, what we are doing. For the, let's say we can select this more pressure as a guide word. Okay. So this is my HAZOP worksheet for the more pressure, for the guide word more pressure. So what may cause the more pressure? I am studying the tank as a node. Before doing this HAZOP study, we need to split the whole process scheme into the nodes, so that the HAZOP study will be streamlined, because doing the HAZOP for the entire plant may be too difficult. Our case, it is a simple one, inlet line and the diesel tank and outgoing line. But think about the whole process plant, it will be too difficult. So we need to break the whole process plant into the nodes. For each node, we need to apply this guide words. So for an example, in our case, I am taking the diesel tank as a node, and I am applying the guide word of more pressure to that node. So what may cause more pressure within the tank? For an example, while pumping diesel into the tank, that is the incoming line to the diesel, it is kept open. Diesel is getting into the diesel tank. So what happened? Automatically, the vapor space within the diesel tank, which is getting reduced by rise of liquid level, which will result in the increase in the pressure within the tank. So more pressure, the cause will be pumping in diesel will result in the more pressure. So what is the consequence? If I don't have any safeguards, let's see the consequence. Diesel tank may rupture if tank pressure exceed design pressure. So tank is designed for some design pressure. That means that the tank will withstand up to that pressure. If inside the operating pressure exceeding that pressure, there is a chance for this tank will get into rupture, and which may result in the loss of containment. The rupture will result in loss of containment of diesel. Upon ignition, will result in fire accident. Looking into our drawing, existing safeguards, none. It is not the none, actually. I can say that we have an overflow line that may relieve the pressure, but we don't know whether it is sized for this case. As a recommendation, what I'm saying is provide a relief wall to the storage tank. So likewise, we need to go through the entire guide words, and we need to brainstorm what is the cause, what is the consequence, what safeguards we have. If we don't have the adequate safeguards, we can recommend the additional safeguards. So this is how HAZOP will proceed. So we have done the HAZOP, and we have improved the process safety of the plant design. And further, we have LOPA, which is called layer of protection. Okay, what it is? So this is the concept of protecting the plant by means of a onion model. Okay, at the heart of the model is your process design. The very first protection layer is your basic design. For an example, in our case, we are designing the plant to store the diesel and distribute the diesel. So what basic design I have followed? I have selected the correct material of construction to compatible with the diesel, and I have get into the correct design pressure to overcome any overpressure scenario, and I have selected the distribution pump to minimize the leaks from the seal. I have selected the double mechanical seal distribution pump. So these are all the basic design which I have incorporated to prevent any accidents. So above the basic design, what is the next level of protection? That is the basic controls. Recall that P&AD, what I show in the detailed design stage. We have implemented the temperature transmitters, level switches, and all this. These are all the basic controls which will keep that process within the design dimension. And next level, there is a critical alarms and manual intervention. If something goes wrong, this automatic control system fails, the basic control fails, what will be the next level? We have the alarm systems. There is a high level alarm which will give the operator intervention, which will be alerting the operator. So likewise, we have the low level alarm which will give the protection for the pump, dry run. So this is the next level of protection. Above that, we have safety instrumented systems. What is a safety instrumented system? This is again an automated system, but it is independent of the basic controls. The basic controls in our case is we have the level indicator transmitter within the tank, which will control the level. Okay, this is the basic control. Above that, we can implement the independent control loop that is called safety instrumented system. If something malfunction happens within the BPC system, this SIS will come into the picture. It will shut down the system. So that is called safety instrumented system. And above that, we have the next protection layer. There is a physical protection by means of relief devices to avoid any overpressurization of the tank. And the next level, physical protection again, there is a containment system. As you recall, during our HAZID, we have implemented the type. There is a containment system and the plant emergency response. And above the all, if something happens, the loss of containment happens, which may result in the fire or the dispersion, whatever the thing. What is the emergency response we have within the plant boundaries? That is called plant emergency system. If the consequence is going beyond the plant boundary, there is a community emergency response system. Now you can correlate this LOPA concept into the HAZard incident. Okay, they may have the basic design. There is a tank design temperature and the relief valves and the basic controls. If you have the followed up the news articles, you can understand that they have to maintain this styrene below 20 degrees Celsius. So that is a basic control. They may have some controls. And the safety instrument system, I don't know what they had. And the physical protection, yes, they had the relief walls. The entire styrene is relieved through this relief wall. And the physical containment, from the news footages, I understand that they have the type system available within the plant. And plant emergency response, I don't know what system they had. And the community response, in that incident actually happened as a converted into community response, because the styrene, the relieved gas, which traveled beyond the plant boundary, it reached the community. So I foresee there is some lack of community response system. The entire the surrounding population, they are not fully aware of the system, what they handle, and what is the emergency response system available within the plant. So in LOPA, we are studying all these requirements. Okay. For an example, in my diesel tank, I apply all these layers. What layers we have, what I am lagging. If I need to implement the safety instrument system, then the concept of SIL will come into the picture, safety integrity level. Okay, that is again, it is a separate concept which will take more than one day to discuss. I'm not touching up the things, but this is the concept of it. Okay, with this, I am moving on. So we have discussed all these things up to this containment. Okay, now we are into plant emergency response. If something happens with all these protection measures, what we are doing? Before to that one, we need to assess what effect it may result. Okay, so that's where we are getting into the consequence analysis. In our case, for an example, with all these protection measures, let a leak happens, the diesel happens. Then further, what it may result in? Okay, it may result in a dispersion. That means diesel which is leaked out of the system, which may vaporize, and it will result in a flammable gas cloud. And pool fire, if the diesel ignited, it may result in a pool fire. Jet fire, if the diesel leak is happening as a jet instead of a pool. For an example, if the diesel leak is happening on the discharge side of the circulation pump, which is at high pressure, then it will be releasing as a jet. So if it is ignited, it will result in a jet fire. And explosion, if the released diesel vapor cloud, if it is getting ignited as a cloud, it is ignited, what will be the explosion? In the dispersion, we have both flammability as well as a toxicity. For an example, again to the Vizag incident, the styrene, which is flammable as well as toxic. Fortunately, there is no fire incident happened on the accident. It is only the toxic cloud. So we need to assess all these things. So how we are going to assess? We have the sophisticated software for doing this job. So one of the software is the PAST. So the typical output, how it will be looking, this is the way it is looking up. So this is the consequence for dispersion. For an example, I have the leak at the origin of 0, 0 at the elevation of some 1 meter, I can say. If the leak is happening, I am getting the LFL up to this point. That means that in the downwind, I am getting around some 9.5 meter is my LFL cloud, and this is my cloud width. Okay, so like the same way you can generate for toxicity. So for an example, this case is for hydrogen. So hydrogen, there is no toxicity is applicable, it is only the flammability. So I have generated for the LFL value of 4000 ppm, so 40,000 ppm. Okay, likewise we can generate for toxic chemicals. Okay, the next will be the pool fire. For an example, I have simulated for some other liquid flammable material. If that is ignited, what will be my radiation level from the pool? So that will be given as a result in this graph. And likewise for the jet fire, what will be my radiation distances? Likewise for explosion, what will be my overpressure? So based on this overpressure, we need to locate our buildings and other vulnerable objects outside this explosion overpressure criteria. So this consequent analysis will help you to plan your plant emergency system as well as community emergency response systems. For an example, if your consequence says this distance for this dispersion, pool fire, jet fire, explosion, which is all this distance are within my plant boundary, means that means that it is the any effect, it is not traveling beyond the plant boundary. So we need to develop the plant emergency response plans accordingly. If it is going beyond the boundary, we need to look into the community emergency responses. Okay, with this one we are moving to the next concept. So what is this concept? Before that, I am just showing one picture. If I ask somebody to define what it is, the obvious answer is a basket full of apples. Okay, so is there any other definition can be? Somebody may say that a basket full of green and red apple. Okay, this is how this picture can be defined. Okay, now move on to the next picture. I have this picture and I am asking the same person, can you define this picture? This time the definition may be something more concrete. The person can say that a box containing 12 apples. Out of 12 apples, 4 are green and balance 8 are red. Can you see the difference between the definition of these two pictures? The first one, it is saying qualitative. We can say basket full of apples. We cannot define more than that. But in second case, we are defining in terms of numbers. A box of apple, 12 apples. A box of 12 apples which contains out of 12, 4 is green and 8 is red. You see the difference. See, this is where we are getting into the quantitative risk analysis. By saying quantitative, now we are getting into numerics. Up to this point, from the start of my presentation, I have speaking a generic term hazard, generic term dispersion, generic term fire, but I don't give it in terms of numbers. For an example, if it is fire happens, how much distance you can see the radiation of so-and-so radiation, or how much distance the LFL will happen. And again, if a fire happens, is it affecting the people? If it is affecting the people, how many people are affected? So those things will be dealt with the quantitative risk analysis or assessment. Okay. So what is this QRA? QRA provides a numerical measure of the risk a facility or operation poses to the public, to site workers, or on-site and or off-site equipment. So by definition, risk is a function of frequency and consequence. So again, consequence, as we discussed in the previous slide, consequence again is a function of property of material handle. For an example, is it flammable or toxic? If it's inflammable, what is its flash point? Is it easily ignitable or less ignitable? Likewise, leak hole size. What is the hole size where the leak is happening? and isolated section volume. For an example, if we assume the leak from the diesel storage tank, what is the capacity of the diesel storage tank? If you recall, at the starting of the webinar, I mentioned that if the tank is 100 liters capacity, the consequence will be less. If it is a 1000 liter capacity, there is isolated section volume is high, the consequence will be severe. So again, consequence is a function of all these things. This I have listed few things. Likewise, a number of things are there. Likewise, frequency is a function of leak frequency. For an example, again, the diesel tank leakage. If leak is happening means how frequent it can happen. What are all the leak sources? Okay, all those things will be assessed in the leak frequency. Once the leak is happened, it is not getting ignited for all time. Okay, we should have some probability of ignition. Okay, it may ignite or may not ignite depending upon number of factors. Likewise, probability of human presence on time of event occurs. Even if it is ignited, is it affecting the person or not? It is depending upon whether the person is standing on the time of the event the fire is happening, or he is stationed somewhere away. Likewise, number of factors need to be studied to get into the risk. Again, this QRA is a complex subject, which itself requires a detailed discussion. I'm not getting into that part. So I'm just giving you what is the concept behind the QRA, doing the QRA. Again, as I told, it is done by the softwares by inputting the consequence, what we get it from the previous slide, and getting the frequency calculated and then fed into the software. So this is how the QRA will progress. Okay, with all these things, we have some sort of defined design which can ready for construction. You can see that two red color walls. What is this? Okay, I did the QRA for this system, and the QRA study given some recommendation. For my diesel tank, if the leak happens, there is the consequence which is not acceptable. So I need to do some modification into my design to contain the leak. So what I did is I have included the ESD wall, okay, emergency shutdown wall, which can be activated during the leak scenario. So that, for an example, let us assume there is a leak happening on downstream of this line. If you don't have this wall, it will go on continue because these walls are manual walls. Okay. Remember the Jaipur incident, IOCL Jaipur incident, the tank pump incident. There they had the walls, even though it is a motorized wall, but that need to be activated on site. It cannot be activated remote from the control room. A person need to go into the site and we need to push the button. Unfortunately, before that site activation is happened, the diesel whatever released from the tank is formed a flammable gas cloud, so that no person cannot enter into the tank. So what happened ultimately? The entire tank content is leaked out, which resulted in a massive fire incident. A costly lesson learned for India. So what I have included the ESD wall here based on my QRA recommendation. So we have somehow a defined and safe system to go for construction. As you see here from the detailed design, what is the improvement we have done? We have included the ESD walls based on the QRA results, and this seal rating of the ESD wall that will be coming from the LOPA study. I cannot go on detail into that section. As I told, it is a separate topic to discuss. And as you see here, we have included one improvement here to mobile tank. So without pump to load into some mobile tank. This is an improvement from the detailed state. So, and as you see here, as part of this HAZOP recommendation, we have implemented the relief system here, okay, which is not in the detailed design stage. Okay, so this is how the project is getting mature from the concept to the construction, incorporating process safety aspects, tools, everything. Okay, but this is all the review tools. Apart from that, is up to this point we are concentrating how we can avoid the loss of consequence, or how we can avoid the hazardous events. But there is some more layers available to minimize the consequence. With all these protection measures, something happened, some loss of containment happened. So how I can minimize the consequence effects? That's what we are going to discuss further. The first thing is fire and gas reduction system. So whenever there is a leak happens, the very first protection layer in place is fire and gas reduction system. If it is a volatile component or is a gas, we have the gas detectors which will give the alarm to the operator, alert the operator. Or if it is converted into the fire, then we have the fire detectors. Okay. Now let us implement these systems into our design. So before that, we have listed down what are all the detectors available here. For the fire, we have the three types: flame detectors, smoke detectors, heat detectors. Flame detector, it is working on the principle of optics by seeing the flame, and these two, smoke and heat detectors, that is based on the product of the fire. That is the product of the fire is a smoke. If there is a smoke, if there is a smoke means there is a fire is there. Likewise, if you measure your heat means there is a fire is there. So these two detectors are based on the product of fire, and this is the fire itself. And likewise for gas reduction, we have flammable gas reduction, toxic gas reduction, and H2S gas reduction, or any specific gas reduction we can implement. So now, how do we implement this into our system? We have this ready for construction plan. Now I am going to implement the detectors. So first I have implemented flame detectors. I have placed two flame detectors to cover this tank, and I have placed two detectors for this pump. Why? This is a possible leak source, the mechanical seal and other things. This is a possible leak source where we have an overflow line. So that's why I have placed my detectors around these two possible leak sources. Likewise, I'm placing my gas detectors. Again, I'm putting it on the pump, which is a possible diesel leak source. There is a mechanical seal of the pump. So this looks so simple for this system, but as for a whole process plan, it will be a laborious job, and it requires expertise and skills for placing these detectors. Okay. And what next I have? Hazardous area classification. What it is? The leak is happened, and FNG detector is failed to act, or it is failed to detect somehow. So there is a next consequence. Maybe the flammable cloud may get into the fire. So this is a typical fire triangle. Everybody knows about this, hopefully. So for any fire, we need oxygen, fuel, and ignition source. As you know that fire is an reaction between the fuel and oxygen. That is an oxidation reaction. You can say that. So to initiate that reaction, we need to have the ignition source or energy. So what we are going to do with this hazardous area classification? For any process, we cannot eliminate this fuel and oxygen. For example, in our case, diesel, which is an combustible material, which is a fuel. Our whole purpose of the plant is to handle this diesel. So we cannot eliminate the diesel in our system. Likewise, oxygen. Oxygen is everywhere in the atmosphere. We cannot eliminate oxygen. So only possible thing is we need to control the ignition sources. So how this ignition source is related to the hazardous area classification? Yes. First we look into the definition. What is hazardous area classification? Hazardous area is defined as a three-dimensional space in which flammable atmosphere may be expected to present. So what we are going to do, we are going to define what may be the flammable atmosphere around my system based on the material what I handle, or based on the flash point or the physical properties of the material what I handle, and based on the operating temperature and pressure. So I am defining the flammable, three-dimensional flammable atmosphere around my system. So that if I define that one, then I need to control the ignition sources within that cloud, three-dimensional cloud. So what flammable ignition source I can foresee? Any open flame. For an example, I cannot place a diesel tank near the fire heater, let us say furnace, because there is an open flame is there. It is an ignition source. Likewise, I cannot place normal electrical items into that flammable cloud. And the normal electrical items are prone for generating spark. So I need to go for specialized electrical items. So we are going to first define the flammable atmosphere, then we are controlling the ignitable sources which is going to be present within that flammable atmosphere. How I can define that atmosphere, flammable atmosphere? Yes, we have the process standards, and again it is a separate subject for discussion. So I'm just giving up the introduction of that one. So what we are going to do, we are going to zone classify my system. So what zone classification? Zone 0 corresponds to part of hazardous area in which a flammable atmosphere is continuously present. That is 24/7, there is a flammable atmosphere. Flammable atmosphere means we have the field as well as the oxygen. That is a flammable atmosphere. If that is there, I am defining that as a zone 0. Likewise, zone 1, that is likely. That is not 24/7. In a day, sometime it is available, sometime it is not there. Likewise, zone 2, it is not likely to occur during the normal operation. However, it is existing. Okay. With this, let us do the zone classification for our system. I'm just copy pasting from the code. So this is my diesel tank. This is my diesel liquid level inside the tank. Above the diesel tank, it is a diesel vapor as well as air, because the diesel tank is open to atmosphere. You remember the overflow line and the relief valves, which are all open to atmosphere. Okay. So when I pump out the diesel, the liquid level will go down. On that time, the air, outside air, will get into the tank. When I pump back the diesel, the level will go increase. Okay. On the time, this space will have air as well as the diesel vapor. That is an 24/7. We have the flammable atmosphere. So inside the tank, we should have zone 0. Remember the relief valve. So relief valve will activate whenever there is a overpressure. So whenever there is activating, it is releasing the diesel vapor. In that case, we don't have the diesel vapor 24/7, but it is percent likely. So what I'm doing, I am classifying this area as a zone 1. And zone 2, but it is not likely available during the normal operation. For an example, if there is a leak happens in the level gauge, then the diesel is leaking, then it will result in the cloud. So around the tank, I am classifying as zone 2. Once this is done, then electrical people will get into the picture. They will select the electrical apparatus according to the classified systems. Okay. So we have completed the hazardous area classification, one improvement on minimizing the consequence. What next we have? Active fire protection. Yes, what it is active fire protection? Active fire protection system is defined as those systems wherein an action must be executed either manually or automatically before the system will operate. So we have the next protection layer, that is the water fire protection system. If above the all, if there is a fire happen, how I can minimize the damage happening due to the fire, where this active fire protection system come into the picture. So it describes the firefighting systems and equipment to be put in place during the fire incident. Such system includes deluge system, water monitors, hydrants, mobile fire monitors, coke systems. So this is the typical fire water system. It starts with the fire water tank, which is sized in such a way to fight a fire for the defined duration, and it is having the jacket pump and the fire water pump, and we have the delivery system into a loop network where we have the monitors, deluge, hydrants. Okay, so this entire system is pressurized with the jacket pump running. So there will be a set point. Below the set point, it will automatically start a fire water pump. If the jacket pump is not sufficient to maintain the pressure, the fire water pump will automatically start in and will stop supplying the fire water. Okay. So in this system, we have this monitor and hydrants, which is again need to be activated manually. The person need to go and you need to connect the hose to the hydrant. Then you need to direct the water hose into the fire. Likewise, for a monitor, the person need to go into the field and you need to move the monitor nozzle in such a way to fight the fire. And in deluge, again, we have the manual activation as well as the automatic activation. Deluge is something like pouring a water in a immediate effect all around the equipment. Again, this system, the study and the design of this system, that is an entirely one day or multiple days we need to have get into them. But this is the basic, very basic. The thing is, we have the active firefighting system as a protection layer. So with this active fire protection system, how it will be my diesel tank will look like. As you see here, we have our diesel tank here. Unfortunately, this picture is not having the diesel pump, but it is giving the details of the fire protection system what we designed. As you see here, these are all the deluge nozzles. which is activated from this control panel, and we have the monitor located here, and we have the foam pourers. This is one of the another one firefighting tool, which will deliver the foam into the dike area. For an example, if there is leak happens here, there is a diesel pool is here. If I apply the foam over the pool, I am eliminating the contact of fuel with oxygen, because in between we have the foam layer, like the way we have extinguishing the fire. Likewise, we have the foam pourers for this tank. If this tank is a floating wood tank, this example is a floating wood tank, so that we have the foam pourers on the above the. So this is how the typical system will look like when we have the complete design for this fire system. Okay, with this one, our next protection layer is a passive fire protection. What we are going to do in the passive fire protection? What is the difference between passive and active fire protection? Passive fireproofing is for the protection against the adverse thermal effects of fire for a limited period and limited degree of exposure. It is a protective measure to improve the capacity of equipment and its support structure to maintain its structural integrity. See, any fire will result in the reduction of structural ability of the metal components. If the metal component is exposed to the fire, it will eventually lose its strength as the temperature increases. What we are going to do here, we are applying the protective coating over the metal surface so that it will be the heat input to the metal structure is limited. So how it looks, it is like this is the actual site picture. Theoretically, like that, we have this I-beam, which is a metal load bearing component. If this I-beam failures, it may result in additional loss of containment. If this I-beam is supporting any flammable material containing vessels or pipeline, so I am applying the PFP coating above this I-beam so that if there is a fire happening in the nearby equipment, this I-beam cannot lose its strength. So this is how practically it will be looks like the passive fire protection coating. Fireproofing applied to vessels, structures, buildings, walls, and pipe supports. Okay, where we have this flammable material containing systems. The length of time during which an element needs to maintain its integrity depends on local circumstances. The type of coating, that selection is based on how much time I need to protect this member. Okay, how much heat gradient it needs to withstand. All those factors are the defining factors on selecting this PFP coating material. Okay, with this, I am moving on to the next one layer, engineering control of noise. Generally, noise is considered, people consider this as a occupational hazard. Yes, it is an occupational hazard. However, prevention of this noise, we need to take an engineering control. That cannot be controlled by the occupational safety measures. We need to take it during the engineering stages. So that's why it is considered as part of the process safety activity in the engineering industry, engineering sector. So what is the limitation? The normal limit is 90 dB and 115 dB for the occasional. For an example, if we have the PSV, which is releasing once in a while, on that time we can exceed this 90 dB normal limit. That too, we cannot exceed 115 dB. So these noise levels we need to access during the design stage. For an example, in our case, we have the pump, which may be resulting in a noise, and we need to ensure that the diesel distribution from noise level is within this 90 dB. If it is exceeding, what I can do, we need to go with the enclosures, acoustic enclosures, so that the noise cannot be, outside noise will be limited to 90 dB. So that is the another one protection layer. That is, again, it is not on the exactly on the process safety. It is an occupational safety, however considered as part of the process safety also. Okay, with all these things, we have a number of tools and activities we have discussed. So how it can be delivered to the downstream my fellow engineers or to the clients by means of safety. So hazardous area classification layout, where I will show all my clouds. FNG detector layout, where I will show my location of the detectors and the type of detectors. Active fire protection, which shows the location of my firefighting system, location of my monitors, hydrants. Likewise, passive fire protection layout, that will show what members of passive fire protector. And noise zone layout, which will use which is the high noise area, which is a low noise area. In high noise area, what protection further from the occupational aspects we need to do. Escape route layout, if there is a fire incident happens, what will be my escape route. Safety equipment layout, like the portable extinguisher, I have not covered those things. Portable extinguisher and other things. Safety sign layout, these are all the minimum layouts things I need to do as a process in this project. Okay, with these things we are almost at the end. What kind of softwares as a process safety engineer we are using? Pipette. So this is the software we use for fire water system design, hydraulic analysis of the system. Past Safety, and this is for the consequence analysis, QRA. Ganda, this is for noise study. PHA Pro, this is for HAZID, HAZOP, LOPA. Any review process we can use this PHA Pro to record the things. It is something like Excel kind of software, but it is a sophisticated one. So with this, I am finishing my webinar. We are into 7:40, 10 minutes. I have taken extra. Now I am giving back to Gokul. Gokul, I am ready for answering any questions.
Yes, sir. I think thank you so much. I think for your informative and wonderful session. I think so many safety concepts we have seen here and protective methods also, and also like the basic. It's an introduction, so we need to learn more. So definitely, I think today our the fellow engineers and participants would have enjoyed much, and we have quite number of boring questions was there. I think there are some chemical engineers also. More chemical engineers are there. I think I will just read out few of the questions.
Okay.
Okay, this is from Balamurugan. How far carrying out the QRA in concept stage would help me to design a safer facility, especially for the given scope of work. Just to contemplate the use of QRA in various phases of project life cycle.
Okay. Doing QRA in concept stage, as you see here, when I am looking for the QRA, I am looking for the detail. For an example, I need to calculate the leak frequency. Leak frequency means I need to look into have the P and ID. What are all the elements I have in my piping system? For an example, if I have the leak, if I have the valve, for an example, valve is one of the leak source. For an example, stem of the valve, it is prone for leak. Okay. So to calculate my leak frequency, I need to have the entire detail of my system. That will be only available to me at the detailed design stage. Okay. As you see to the presentation slides, at the concept stage, we have only the key elements, key equipments. We don't have the detail. So if I do the QRA on the concept stage, that may not be giving you the correct results. Okay. That may be over conservative. Okay. So in terms of leak frequency or the consequences, everything is not fixed up. So if we do the QRA on a detailed design stage, we have all this design freeze so that we can do the. But as an experienced engineer, we may need to include all this foreseen recommendation in the design itself. For an example, the ESD board, what I shown, that may be included in my detailed design before going to QRA itself. Because I know as a process engineer that may come into the later stage. Instead of waiting for that one, I will include the detailed design itself. In that case, the QRA will be just a verification aspect. Okay. So this is to answer your first question. On the second question on the run plan, yes, we can do the QRA for the run plan. In fact, there is some Indian regulations there to revisit the QRA or update the QRA in the given gap. For an example, in the Vizag plant also, there is an speculation stating that their QRA is not updated to foresee that to reflect the current scenario of what they have in the plant. So that is one of the news article I have read that they have not updated their QRA. So any run plan, they need to periodically do the re-HAZOP, validation HAZOP, as well as the QRA, validation. Hope this answers your question.
Yes. We have another question from Mr. Srinivas K. So a part of LOPA, does we take credit for contaminant? The contaminant that is bud or combing will still have a potential chance for pool fire.
Okay. In the LOPA, the layers, protection layer, what you define, that need to be agreed in agreement with your end client. Okay. See, all these process concepts that are all developed in the last 10 years, I can say. Okay, maybe after these Bhopal incident, maybe 10 to 15 years, something like that. So all are under development. Nothing is become as a standard rule. For an example, if you are designing a relief system, we have the API or ASME standard. You need to follow. This is a code you need to follow. Likewise, we don't have such a system for process safety. Okay, for HAZOP, the guide words, what guide words I will select, what guide words I can leave it. That is an agreement between you and your client, end client. Likewise, for LOPA, whether I can take a credit for containment system or not, you need to agree with your client. As a process safety engineer, I can say that I can take some credit.
What is the fireproof material used for fireproofing?
Yes, there is a number of options available: concrete based one, imprisonment paints based one, all those things, epoxy based ones. See, the basic concept, the concrete based, it will be bulk material applied to the mainly to the structurals. Okay, but in case of epoxy or other paints, it will be thin in the nature. But whenever there is a fire embedded on these paints, it will be charred. It will create a thick coating of charred carbon, which will further prevent the heat penetration into the member. So you can just Google it. You can find a number of materials based on the vendors.
Will it not increase the load on the structures?
Yes, that also taken care. That is the what is it? The structural engineers need to take care. They will be looking for the process safety engineer to give this. What is my thickness of this PFP coating? Accordingly, they need to define the structural number, design the structural.
Thank you, sir.
Yes, sir. So we have one question from SK Swami. So in the Vizag plant, what acid leak and toxic gas detection alarm is installed or not?
That we don't know, because we are the outside community. We don't know what is there inside the plant. But what I understand is styrene is a monomer, okay, which need to be cooled at below 20 degrees Celsius. And it is a tendency to self-polymerize. In fact, they are doing the polystyrene as a product. That means styrene polymerization. Okay, that is a process. In that case, what I foresee is they have stored the styrene in the storage tank. Something went wrong. The temperature, storage temperature, gone beyond that auto polymerization temperature, which may result in a runaway reaction. And that runaway reaction result in a heat liberation that may heat up the balanced styrene, and the pressure inside the tank went high, which result in the PSC opening of relief valve and release of styrene. That is what my understanding, but we need to wait for these any study reports coming out from the government side.
Yes, sir. We have one more from Ponram. So he said, as you said, vapor cloud explosion for diesel is possible.
Again, I have, for the example purpose, I have used the diesel. Diesel from the flashpoint perspective, it is falling under the combustible. That means that it is forming a gas cloud, but getting ignited is very rare chances. So you cannot say that it is possible for diesel, okay, but it is possible for any gaseous species.
Okay, so that's all. I think questions from chat box is over. So
Okay,
we may request any audience, one or two. I think if they wanted to directly, they can ask. Before asking, they can introduce themselves and they can ask.
Mr. Elango, good evening. Ponram here.
Good evening, Ponram.
Yeah, I'm a process engineer and proud to say I'm your ex-colleague also. Actually, you answered my query. The thing is, what I understand is for diesel, there won't be any vapor explosion, right?
Yes.
Okay, fine.
See, vapor explosion, there is number of factors need to be considered. For an example, if I place my diesel tank or any gaseous thing in an open plain plant, okay, in that case, it is an flashback fire, okay. Yeah, explosion need to happen. You should have the confinement. For an example, let us assume the gas cloud in an open space, and I am igniting the gas cloud, and there will be some effect. Let us assume the same gas cloud inside a room, and I am igniting this. The consequence should be different for the two cases. For the first case, you don't get any explosion overpressure because it is on the open space, okay. That ignition will result in a flash fire. But inside the room, it will result in a overpressure because the combustion products, that is the CO2, which is coming out of this burning of this gas cloud, will be having the higher volume, which will result in expansion, and it is contained by the room. You can see the pressure which will be acting on the room wall. So in the second case, you have the overpressure, and in the first case, you don't have the overpressure. So it is not simply like that. If you have the gas cloud, you will have the explosion. No, not like that. If you have the gas cloud, you have the containment. And if you have the what is the ignition source, location of ignition source, all those factors will need to be taken care.
Mr. Elangovan, Elangovan from Abu Dhabi.
Yes.
Yeah, technical safety concepts as part of PSM very well explained in simple and effective manner.
Thank you.
Thanks for the session. Actually, I never attended the PSM session in this simplest way possible. Well explained. Thank you very much.
Thank you.
Sir, Elangovan, this is Soma. Can you hear
Good
me?
morning, sir.
Soma.
Good evening, sir.
Good
Yes,
evening.
sir.
I'm Soma. I'm ex-colleague of Elangovan, working with Technip Abu Dhabi. Thank you, Elangovan. It's a wonderful session. Only
You,
one question. It is you haven't covered about the FERA. It must be an important, I feel, in my opinion.
Okay.
FERA, fire explosion and risk assessment.
Yes, sir. What I thought is I have given the title as a consequence analysis. That consequence analysis can be referred in a number of different ways. For an example, fire and explosion analysis or the building risk analysis. But ultimately, we are looking into the consequence and how the consequence is impacting my people and property. So the title may be different. Yes, I agree.
Good. Okay, Elangovan. Thanks. Very good.
Yeah. Is there any final question, sir? I think before we close up.
Maybe one more. We can take one more if anybody is interested.
Mr. Elango.
Yes.
Yeah, actually, this is again Ponram. Since you discussed about that vapor cloud, I just curious to know some kind of hydrogen explosion, hydrogen cloud explosion and all happened. I just experienced about that. Could you please tell me how to avoid if any hydrogen cloud, for example, any other cloud also maybe. Hydrogen cloud is a very dangerous one since it has no color and no odor.
Yes.
Any kind of vapor explosion, how to handle it as a process?
Okay. See, if you want this kind of level of detailing, one way is to ensure your ventilation. Okay. So if you are where you are placing your plant, let us assume there is a leak happened, and you need to input this plant model into the CFD, and based on the prevailing wind velocity, if there is a leak happens, whether it will be dispersed below to the LFL value or there is a chance for getting the LFL cloud. Okay, that thing you need to do with the CFD analysis, and you can ensure that yes, even if the leak happens, it won't result in ignition. Even if the ignition happens, the explosion overpressure will be not damaging any of the vehicle. We can do it, but all these things in the safety, everything is effort and money and the detailing. Okay, if you want to go to the CFD analysis, you need to have all these details and the time and the resource.
Mr. Hello, this is Murali.
Yes, no problem. Go ahead.
I'm Muralidharan. I've worked as a chemical in SR engineering.
Yes, Muralidharan.
We have done projects also, expansion of refinery. This thing. My question is the flare systems.
Yes.
Flare systems is not discussed.
Yes, I agree. That is again. This is an 1 hour session. I have given with the 1 hour. I have taken 1 hour 1 hour 10 minutes. I think. So this is. I cannot accommodate everything into this session. Okay. I thought this is part of this consequence analysis. Yes, you can assess the flare also. Again, this is the flare radiation analysis part of the consequence. Again, also there also we are going to assess what is the radiation level and it is impacting any people or flare. Yes, I agree. That should be appeared as a separate slide. Maybe in the next presentation I will include, but it's again depending upon the time for which I am allowed.
Yeah, we understand. Thank you, sir. Thank you.
Yes, sir. I think we had a very good session with the various participants who have given their question and questionnaire also. So definitely, I think we can plan one more session in advance mode with the approval of a chairman, the phase 2 manner. So maybe after this next month also, we will try to do that because the audience are so much of curious. And I think as our speaker also requested, I think some more non-IEA members also is there in the forum. So for them, I think the benefits of IEI and how the IEI, the functions of IEI, if our chairman can explain, so we can able to bring them also under the cloud of IEI. I hope. So I just give to our chairman. So with the concluding remarks, so that we can close. Sir, please.
Thank you, Gokul. It's a wonderful session by Elangovan sir. Thank you once again, Elangovan sir.
Thank you, sir.
It's a great session. As far as IEI, it's a 100 years old organization, right? 1920 it started. Right now that 20 years, 100 years celebration we are going on. So all over the India is 124 centers here. The main headquarters is Calcutta. That Tamil Nadu State Center located in Chennai, and under the Tamil Nadu State Center we have 16 local centers are there, and then different membership is there. First one is AMIE, that is Associate Member Institution of Engineers. Those who are passed out engineering graduate and is eligible to get AMI and Chartered Engineer certificate. And then professional engineers also is there, and then once 5 years experience, you can eligible to get the professional engineers. International professional engineers also in we are doing. For that international professional engineers, we are conducting the exams. Based on the exam result, they are awarding that international professional engineers. The next membership is a member institution of engineers. Those who are completed 30 years and then 10 years, 9 years experience in the field. So after degree, 9 years experience in the field, they are eligible to MIE. And then next one is the fellow institution of engineers, FIE. FIEs who are completed after engineering 20 years, and then age is completed 40 years. And then one more criteria, the minimum salary should be monthly more than 2 lakhs rupees. Then if it is a company owner and like that, more than 24 lakhs turnover company is there's a proprietary company, they are eligible to get FIE. If it is a government employees, more than SC, that is super engineer, it's eligible to FIE. These are all the membership and other facilities are there. Regularly, the Institution of Engineers is conducting this type of program regularly, and then 1 day program, and then 2 day seminars, even international conference also we are conducting. Apart from that, the student membership also is available. Every colleges we are having that student memberships. All the students first year itself they can join as a student membership. After 4 years, they can able to join as a they able to get a AMI degree also. With this, today I think the session is wonderful. Bala, Mr. Bala, Dr. Bala is there. I think okay, Gokul, just to give the
yeah. So yes, sir. Thank you so much. I think for your IEI opening remarks. Definitely, I think we had a very good participants. I think starts with even it was ended with 100 more participants. I think so many people would have not able to join it. We have already said them also. They can also join in the YouTube. So definitely, it is a wonderful session in the Sunday evening.
1 minute, Gokul.
Yes,
Right
sir.
now, actually, we are bought WebEx at more than that is 100,000 participants license. Maybe in the next session, we'll go to the done by the WebEx, and the participants is 1,000 participants.
Okay. Great.
Chairman sir,
More number of participants.
Chairman
Will be
sir,
there.
Mr. Gogol,
Yes, yes.
Mr. Gogol, this speaker covered the topic very nicely. I'm Karpasamy from Trichy.
Yes, sir. Yes, sir.
From the
Thank you.
beginning,
Thank
I
you,
was
sir.
watching. He has nicely covered from the design to the final project. You know,
Yes, sir. Yes,
the
sir.
points except that flare system, he covered everything. Thank you.
Yeah. Thank you.
Thank
Thank
you,
you.
sir.
Thank you. So thank you so much, sir, for your presence on Sunday evening. Also, to participants and our members of IEA. So I think they had a wonderful session of 2 hours. So definitely, I think we will have more sessions for the coming days also. Thank you. Thank you so much.
Thank you.
Thank you.
Thank you. So I'm signing off. Bye now.
Thank you. Thank you, Elangovan.